Do you know that you can keep a secret or a password safe just by hashing it? Hashing is a one-way irreversible function. An input is transformed into a fixed set of characters. Doing so, you are never saving the original value, and nowadays most systems store this hash version of a password. Today we'll compare the best hashing algorithms and dive into the world of password encoders. In the past, passwords were stored in plain text. People believed that was enough since credentials were needed to access the data itself. A common attack to this approach is SQL injection, which is usually prevented now with architectural decisions, like using repositories and parameterized queries. Hibernate uses prepare statements that separate SQL structure from user input, treating the input as data rather than executable code. So do your best to avoid string concatenation in queries inside your code. Later, hashing like SHA-256 was used. The issue with this is that those hashes are vulnerable to rainbow tables. Rainbow tables are pre-computed tables of common passwords with equals to common hashes. A defense against these rainbow tables is to salt your password. You will mask your input with a random value. For example, if you like to use password 123 or ABC and you will then salt it with a random number, it will become very difficult to guess it. SHA-256 is no longer secure, since nowadays it is possible to perform millions of hash calculations per second. A better approach is adaptive hashing. This allows computational cost configuration, time and/or memory, making it expensive for attackers to guess passwords. You can adjust the verification cost over time by following your hardware improvements. It is recommended to tune the work factor, the cost of the hash function, so the process of verifying a password takes about 1 second, a number that should balance user experience and system security. Instead of checking the password every time, it is much more secure to use short-term credentials, like tokens. They can be validated faster without losing any security value. Spring Security default encoder for DelegatingPasswordEncoder is BCrypt. It can be customized with 3 parameters: a version, a strength, a number between 4 and 31, the default is 10, and a random salt, which adds uniqueness to our hash result. If we check our users table, the password bamboo is encoded at BCrypt version, cost factor, a salt, a random, and hash password output. SCrypt allows more parameters to be defined: CPU cost, memory cost, parallelization, how many threads are run in the same time to generate the key length, and salt length. Argon2 is the winner of a password hashing competition back in 2015. Is the strongest and the most difficult to attack. PBKDF2 is the weakest, the fastest, and the oldest in the list. It's recommended only for legacy systems. It's useful if you're working for the US government or the military where BCrypt is not compliant, even though it's more secure. Password encoder is actually a hasher, not an encoder. It's irreversible and used to secure passwords. It has 2 main duties: validating the encoded password, meaning that compares the provided password hash against the stored hash, and hashing a password using a specific algorithm. BCrypt is the default. If we want to hash the password again with a stronger algorithm, we can use the upgrade encoding method to check if the parameters are strong enough, as we defined earlier in the password encoder bin. For BCrypt, we will check the number of iterations. For SCrypt, the CPU, memory cost, and parallelization parameters, and for Argon2, memory and iterations. Spring chooses DelegatingPasswordEncoder with BCrypt as default. Its storage format is brackets, ed, encoded password. Although the format is visible, this does not help hackers guess passwords because algorithms are public and the format is well known. Security comes from the algorithm in strength itself. This tool allows applications to support multiple password encoding algorithms. All users can continue using their existing encryption. So DelegatingPasswordEncoder, it's an implementation of the password encoder interface. It contains itself a password encoder attribute. Let's check its constructor. Here we have id to password encoder, a mapped list that contains all the password encoders implementations available. This mapping will then link to the correct encoder implementation to use, based on the prefix of each stored password, like nope or BCrypt. The encode method will then redirect us to the correct password encoder implementation we mapped before. The same will happen with the matches method. Let's build a new branch from our branch 6. You can find the repository link in the description. We can create a bin of type password encoder that contains a list of encoders. We can go into the user configuration file and customize our simple password encoder just by adding a couple of them in a map. We can give a fancy key name to our encoders and add the default encoder to the delegating password encoder, which it will be returned. And let's clean some data in our table, just adding a delete all method at the beginning of the init users. You can see that when we run the application, the password is saved in BCrypt format. Let's now try to tune our password encoders in a way it takes roughly 1 second to verify a password. I will twist our users a bit and assign SCrypt as our password encoder. We need a bouncy castle library in order to access SCrypt. Let's add SCrypt as default encoder with default values. A fast way to check how long the matches method can take is to decorate then our encoder. Basically, we just add the timing functionality. I will create timing password decorator encoder in the utility folder. And update the user config. With our configuration, our call will take a lot less than 1000 milliseconds. Let's experiment with our hardware and tuning parameters to achieve the OWASP recommended 1 second verification time. On my MacBook M3 Pro, I can reach this target by multiplying by 8 the default CPU settings. For example, since our first verification run took around 100 milliseconds, let's add 500,000. It's a bit too much, so probably the best user experience in this case will be multiplied by 7. The real challenge with complex application, however, is finding the right balance, pushing CPU and memory usage just enough without overwhelming the system. Instead of manually creating a list of encoders, you can use password encoder factories. This code behaves as before, with BCrypt as default encoder. Password encoder factories will create password encoders based on the prefix found in the password. Otherwise, a no password encoder error is thrown. There is a public service, Have I Been Pwned API, that helps improve our security by preventing users from using breached password. This API allows you to check if your email or password was exposed in a known data breach. Spring Security will provide an integration with this API so we can implement custom logic in a compromised password checker bean in order to redirect users, for example, to a reset password page. Today, we explored how modern hashing algorithms like BCrypt, SCrypt, and Argon2 keep user data safe, and how Spring Security Password Encoder interface make it easy to implement strong password hashing in a Spring application. If you found this video helpful, don't forget to like, subscribe, and hit the bell for more deep dives into the Spring Security best practices. See you in the next video.